All right, for scalar-valued functions, we're going to find a new interpretation of the derivative that works well with level sets. But in order to do that, we're going to have to overcome some cultural differences. If you maybe look at some old-fashioned calculus books, you're not going to find matrices, you're not going to find linear transformations. This is a bit more modern approach, thinking of derivatives in terms of linear transformations. If you look at old-fashioned books, if you look at books that are more physics-based, you're going to find everything described in terms of vectors. Why is that? Well, the old-fashioned books tend to only look at scalar-valued functions. And in that case, there is a more primitive approach to the derivative. Now, in order to cover that, we're going to need a new definition that reinterprets a derivative using the language of vectors. This is the gradient of a function. For a scalar-valued function on Rn, the gradient is the vectorized derivative. That is, you take the partial derivatives, partial f partial x1 up through partial f partial xn, and you stack them in a vector that is called del f, or maybe grad f. This is the gradient. It is a vector at an input a for whatever values of a you want. Now, if you compare that with what we know as the derivative, namely the linear transformation that has as matrix representation a row matrix of partial derivatives, it looks really the same, but they act differently. The derivative is a linear transformation that acts on vectors at A, whereas the gradient is a vector at A. But as a vector, it's geometric. You can visualize it. You can draw a picture of it. Now, it seems like a formal distinction. I mean, a derivative here, gradient here, row vector, column vector, what? Okay, look, what is nice about the gradient is that you can draw pictures. So let's go ahead and do that. Let's look at the function f of xy equals x squared y minus y squared minus 2xy. What is the gradient of that? That's easy. We just compute partial f partial x, which is going to be 2xy minus 0 minus 2y, and then partial f partial y, which is x squared minus 2y minus 2x. And we stack that into a vector. That's the gradient of f. Now, just like with derivatives, depending on the input, depending on where you evaluate it, you get different things. In this case, you get vectors with different lengths and different magnitudes as shown on this diagram, on this map of the graph of the function, where I've drawn in the level sets for you, and I've drawn a heat map. So the hot colors are larger values of the output. The cool colors are smaller values of the output. And you can look at this and you can see different values of the gradient of f at different points in the domain. So what do you see? Do you notice anything interesting about the magnitudes of these vectors, about the directions of these vectors? This is what gradients are good for.